Thanks. So I will speak about first FPT-Approximation of Branchwidth, and this is joint work with Refinement. Okay. So let's start by looking at the definition of Branchwidth, and in particular a quite generic definition where we have a function f. So let the p be a set and f be a set function from subsets of v to non-negative integers, and we want that this function f is also symmetric. So for any set, the value of this function of the set is the same as the value of this function on the complement of set, which we denote by a bar. And now we say that the branch decomposition of this function f, it's a cubic tree, so tree where each node has a degree 3 or degree 1, which is a leaf, whose leaves correspond to v. So the leaves have a bijection with this set v. And so, for example, here is some example of a set v, a, b, c, d, e, f, g, h, and some and a branch decomposition of some function f on this set v. Okay, and now each edge of this decomposition, you can see it corresponds to some bipartition of this ground set v. So, for example, this edge between nodes u and v corresponds to partition with a, b, c, d on one side and e, f, g, h on the other side. And now we can say that the width of this edge, so which we denote by f of uv, where uv is the edge, is the value of this function on this on either side of this partition. So because it's symmetric, the value on both sides is the same. So, for example, the value of this edge, the width of this edge uv is the value of this function on ABCD, or equivalent to on EFGH. And now we say the width of this decomposition is the maximum width of an edge in this decomposition. And the branch width of this function is the minimum width of a branch decomposition of the function. So this is what we're interested in computing. So given function f, a branch width of f, and as said, branch decomposition. And okay, and let's restrict this function. So what we do in this work, we consider branch width of connectivity function. So we say this kind of set function is a connectivity function if it's a symmetric submodular function. So really, yeah, some people say it's a symmetric submodular function, but we say for priority, we say connectivity function. And yeah, so it's symmetric, like yeah, the value of any set is value of this same as value of this complement, and then it's submodular, it satisfies this submodular inequality. And some examples of connectivity functions whose branch width we are interested in is so first example is a border of an edge set in a graph G. So let's look at the graph G, and let's say for any subset A of edges, let's define some sigma of A, the number of vertices incident to both edges in A and edges in the complement of A. So it's like we have some subgraph, and then the value of this function is like the border of this subgraph with the other edges. And now the branch width of graph G is the branch width of this function sigma G. And another connectivity function which we are interested in is a cut rank in a graph G. So now for cut rank, we say for some vertex set A, we say that the cut rank of this set is the rank of the matrix describing edges going from this set A to the complement of this set. So really it's like, so we have some partition A bar of this graph, and we look at the edges between this partition, and they can be seen as as a matrix, 0-1 matrix, and we can compute the GF2 rank of this matrix. And so the rank width of graph G is defined as the branch width of this cut rank function. So really, if you think about it, so when we have branch decomposition, this is like for rank width, which we say is rank decomposition, then it's like for each edge, you have some vertex partition, and if the width is small, then this edges between this partition are some like low rank matrix. Okay. And so what we do in this work is we give a framework for designing FPT-Approximation algorithms for branch width of connectivity functions. So we have structural results that are generic in the sense that they apply for any connectivity function. And then we have some applications of these structural results. So first application is that we have a two-approximation algorithm for rank width of a graph that also, of course, outputs the corresponding rank decomposition with time complexity quadratic in n, the number of vertices, and double exponential in k, the rank width. And this is first algorithm for rank width where the dependency on n is only quadratic. And then second application is for two-approximation algorithm for graph branch width, and this time with time complexity linear in n and single exponential in k, which is the parameter of the branch width. And of these results, okay, both of them are improve or known results, but this rank width, this algorithm for rank width is I think more important. So let me tell next some background about why rank width is important. So this graph parameter rank width, first it's a more general graph parameter than tree width. So I believe you believe that tree width is important. So I'm trying to say that rank width is somehow, because of this, rank width is also important. So it's more general than tree width. But for tree width, we have that the tree width of a graph is always at least the average degree of the graph. So tree width is not useful for any dense graphs. But rank width can be bounded for dense graph classes. So rank width can be small if you have some dense graph with some nice structures. So for example, cliques have bounded rank width, cographs, distance-related graphs, and K-leaf powers all are important graph classes that are known to have a bounded rank width. Okay, and also if you know the parameter clique width, then really rank width is approximately equivalent to clique width. So if it's like if rank width is bounded, if and only if clique width is bounded, and really the historic thing here is that clique width was introduced first, but then rank width was introduced to give an approximation algorithm for clique width, and still the only known way to approximate clique width is by using rank width. So here, okay, yeah, we have that rank width is, yeah, it's more general parameter than tree width, but what we can use it for? So like there is Korhosen's theorem for tree width. There is also Korhosen's theorem for clique width / rank width, and yeah, I put here quotes because yeah, it's given by Kuusela, Makovsky, and Rotix, not Kuusela only, and this connection of clique width and rank width, and really the introduction of rank width is to Ohm and Seymour. So this theorem says is given a graph with the rank decomposition of width k, any MSO1 definable problem can be solved in quadratic time for fixed k. So really, yeah, f of k times n squared time. And so this includes quite a lot of classical NP-hard cross problems like maximum independent set, maximum clique, dominating set, and k coloring for fixed k, and yeah, and also like optimization variance, and I guess also, okay, I don't know about what the variance, but yeah. Anyway, yeah, but for this theorem, yeah, to use it, you really need this rank decomposition. So without knowing the rank decomposition, you cannot use this Excursion's theorem. And previously, the situation was that that the best known algorithm for computing a rank decomposition, or even like approximate rank decomposition, like, okay, approximate rank decomposition is enough for this result, really. So previously, the best rank approximation algorithm was a cubic time for fixed k, and really there was multiple of these kind of algorithms, but the first of them was given by Ohm in 2008. And so in this work, we improve rank width approximation to quadratic time for fixed k, and and now this gives this theorem that given graph of rank width k without even the decomposition, any MSO1 defined problem can be solved in f of k times n squared time. So yeah, so this is the main application of our result. Okay, so yeah, let me tell before going more details about this our framework that we give in this work. Let me tell about some of the techniques for rank width. And so, well, first thing is we use for obtaining this quadratic time rank width algorithm, we use well-known technique of iterative compression. So we maintain a rank decomposition of width at most 2 times the rank width of a graph. So we insert, so we start with the empty graph and insert variables 1 by 1, and maintain a rank decomposition for this 2 approximation. And specifically, what is important here is we maintain an augmented rank decomposition. So rank decomposition where basically, so for each edge, we have this, each edge of this rank decomposition corresponds to this low rank matrix. So we maintain, basically, if it's like rank k, then we maintain like a 2 to the k times 2 to the k matrix, given like given representatives like of this this rank. And yeah, and what happens here when we raise 1 by 1, inserting one vertex to our augmented rank decomposition, it's easy. We can do it in single exponential time in rank width and linear in n. And then the hard part is that we have now, because we inserted one vertex to an arbitrary place in decomposition, we maybe increased the width of this decomposition. So now we have a rank decomposition of width like 2 times rank width plus 1. So yeah, to improve the width to at most 2 times rank width of G. And yeah, this we do. This is really the novel part of this algorithm. So this we do in time double exponential and rank width and linear in n. And then these steps of inserting more vertex, it's repeated n times and results in the end a quadratic time algorithm. And yeah, the important step here is like I said, this improvement of the width. So this like compression step, So let me talk about this for the rest of this talk. Okay, so here let's state this formally what we want to do. So we want the input is an augmented rank decomposition of a graph of graph G of width k. So now k is like 2 times rank width plus 1, and we want to output either an augmented rank decomposition of width at most k minus 1, so improve the rank with improve the width of this decomposition by 1, or conclude that this given decomposition it was already a 2 approximation, so which is also good. And we want to do this in time complexity double exponential k and linear in n. And of course, here we assume that this graph G is already stored as an associative matrix, because otherwise we wouldn't have time to even read the input. Okay, and so our algorithm, first thing about it that I say is a lot of these approximation algorithms for rank width and branch width and tree width, they're based on Robertson-Seymour type idea of building decomposition top down. So really, the usual idea is to start from the root and then split the graph with some small separator into 2 parts, and then recursively go into the 2 parts and build a decomposition for them. So, but this algorithm, it's not based on this idea. It's instead, it uses some ideas from my recent tree approximation algorithm, so similar ideas. And so instead, what we do, we iteratively improve this given rank decomposition by applying some specific refinement operations. So we say, so we prove that there are some specific operations we can use to improve this rank decomposition if its width is larger than 2 times the rank width. And so basically, the combinatorial framework that we give in this work is that for any connected function f, a branch decomposition that is not a 2 approximation, so whose width is larger than 2 times the branch width, this function can be improved by this specific refinement operation. Okay, and now really this algorithm framework, what it's based on is based on iteratively applying these refinement operations, and because they we might need to use n refinement operations to improve the width by even 1. Then we have this that basically these refinements, they could be directly computed by dynamic programming for like rank width and branch width, but this would result in coordinate time. But instead, we prove some. We give with this framework, we give some amortization techniques that apply with these refinements, and can be used for optimizing this to linear time. Okay, so now I try to explain something about our this framework and this refinement operations, what they look like. So the setting here is we have some connected function f and some branch decomposition t of this function of width, let's say k. And we want to either improve this branch decomposition t or conclude that is already a 2 approximation, so k is at most 2 times the branch width of f. And our structural results result is that yeah, let's say an edge UV in this branch decomposition. Let's say it's heavy edge if it causes the branch width of this decomposition. So if the width of this edge is the same as the width of this decomposition, and we prove that if the width of this decomposition is larger than 2 times the branch width of this function, then this refinement operation can be applied, and it decreases the number of heavy edges and does not increase the width. So really, because at the start there are at most n heavy edges, then applying these refinement operations n times gets rid of all the heavy edges and decreases the width of this decomposition. Okay. Yeah. Now, yeah, let's look at what this refinement operation is like. So this refinement operation is specified by a for tuple where we have some edge r of this branch decomposition. So this is r because I think of this edge as like the root of this branch decomposition, and then we have some tripartition C1, C2, C3 of our ground-set V. And okay, and let's look at an example where we have this root edge R is this edge UV, and then this tripartition of this ground-set is partition ABG here, CEF here, and DH here. And yeah, so we start with this branch decomposition, and what happens with refinement with this specified like this. So first we take 3 copies of this branch decomposition. So let's say copy T1, T2, T3. So and in each of these copies we keep only the leaves from this set C. So in copy T1 we keep only leaves from C1, so here ABG, and copy T2 we keep only leaves from the set C2, so CEF, and copy T3 we keep only DNH, so the leaves in the set C3. And now for each copy we insert a vertex W in this edge between the copies of this in this root edge between U and V. So we have this W1, W2, W3 here. And then what we do, we merge these 3 branch decompositions into one by inserting a new node T to the center node T, and connecting this node W1, W2, W3 to this center node T. And then of course, yeah, what happens now is then we prune the decomposition. So when we have leaves that are not labeled, we prune these leaves, and when we have nodes with degree 2, then we suppress these nodes, and the resulting thing here is like this. Okay, and so this is the definition of this refinement, and I'm not yet arguing that this refinement is in any way useful. Okay, so now let's look at more carefully what happens here. So this is the same example still. So first observation, so for each I, it's CI, C1, C2, C3, there will be edge WI T corresponding to this bipartition between CI and complement of CI. So these edges near this center T will be these edges. And except of course when CI is empty, so CI can be empty here. And then let's say W bar is this cut corresponding to U and V here. So here A, B, C, D on one side. And now second observation, for each I, so for each I in 1, 2, 3, there will be edges corresponding to this cut between CI intersection W and its complement, and CI intersection W bar and its complement. So these edges will be like here. So like this, like here will be like it's a B. So it's like C1 intersection W. Like yeah, here will be like CI intersection W bar here. So this edges like near the root, these edges so yeah, now this slide is just putting this more compactly. So the width of these edges near the center will be like f of CI here in the center, and f of CI intersection W like here, here and there, and f of CI intersection W bar in like here and here and here. And so this will be, so these are the widths of edges near the center. And what we prove is that for any set of set W, so that the f of W, so here this W is like this edge here, there exists this kind of tripartition C1, C2, C3 of V, so that f of CI is smaller than f of W divided by 2, and f of CI intersection W is smaller than f of W, and f of CI intersection W bar is smaller than FW. So really what this means is this: if this f of W, which is like f of UE, if it's larger than 2 times the Branchwidth of this function, then there exists some refinement, some this partition C1, C2, C3 that locally improves this branch decomposition. So improves this decomposition around this root. Okay. And now really the main thing about our framework will be that this local improvement, that the existence of this local improvement implies existence of a global improvement. So let's have this setting where we have this root as UV and this cut W bar, and said the width of this is the width of decomposition. And then we say W improvement is any tripartition of V satisfying this thing that really was guaranteed by this previous theorem. So we know this: if this f of UV is large, then this W improvement exists by the theorem of the previous slide. And now the main structural results that we have is that if there exists W improvement, then there exists some W improvement, maybe some other W improvement, so that refining with this W improvement does not increase the width and decreases the number of edges of width K. So improves this branch decomposition. And then we have that this kind of W improvement, it can be found by selecting the W improvement that optimizes some explicit criteria among all W improvements. So I don't have time to explain what this criteria is, but it's like basically, so primarily we minimize like the maximum of f of CI, and secondarily minimize the number of non-empty CI, and then there is also like third and fourth conditions for selecting this W improvement. But the main message here is anyway that this kind of optimization can be done by dynamic programming over this branch decomposition.
Tuukka, just So I wasn't clear, or I had the impression that this W improvement can't make things worse. So it can, because somehow I thought you, apart from the cuts that you mentioned in 1, 2, and 3 in the slide, that you weren't creating any new cuts when you do the refinement.
So it can make things worse. So yeah, here really doing this refinement, it can really do some quite arbitrary things to this decomposition. So it can make things down. It can make things arbitrary bad. And here we say that okay, let's have this W improvement. Is this kind of refinement that locally improves T? So improves at least around this like center, around this edge UV. And here we don't care, repeat this definition, we don't care what happens like below. And but now the main theorem is that the guarantee that the existence of this kind of local improvement, it guarantees the existence of global improvement. And this global improvement can be found by selecting some specific this local improvement. Yeah.
Makes sense. Thanks.
Okay. Yeah. And I guess, yeah, I don't have any more time. So this was already like 1 hour talk. So let's skip this.
To control the time. Yes, you are out of time.
Yeah. Yeah. So here's some conclusion slide. I want to mention, of course, now the main open problem left by this is, of course, so now this algorithm for rank width, it's optimal when we look only at the number of vertices. But if we also throw in this number of edges m, then can we improve? Can we give an approximation algorithm for rank width with time complexity n plus m times or to the power like 1.9? Okay, that's it. Thanks.